Okay, we're going to go ahead and get started. Thank you everybody for joining us today for this special webinar series. We're going to be covering environmental monitoring, flood warning system telemetry. We'll be focusing on different telemetry options. I'm going to walk through some advantages and disadvantages of all the different options. And then have a summary of all the different options that you can utilize going forward. My name is Charles Jost. I will be moderating the webinar today. We have 3 great speakers that we'll get to shortly and introduce them. Before we get started, just a note, we will be recording this webinar. So if you want to reference this after the fact or share it with someone who was not able to attend, we will record this, and just reach out to us if you would like a link to that recording. Because we are recording it, we're going to go ahead and mute everyone. So everyone is locked in and muted. If you do have questions throughout the webinar, feel free to ask those questions. We have a couple different ways that you can do that. You can send and submit your questions through the aptly named questions box there. Someone will either respond back to your question directly and through the text box, or we'll ask it or work it in throughout the webinar. At the end of the webinar, we will allow people to unmute themselves, and they can ask their question directly if we have time remaining at the end. Also, if you come up with a question after the fact, or you don't feel comfortable submitting questions through either of those channels, we have contact information up here at the bottom left there. Feel free to reach out to us. We'll be more than happy to answer any questions, as well as provide any information about anything that you see here today. And with that, we'll get started. So we're going to introduce our speakers here. We have a great slate of speakers combined. They have about 80 years of experience in the hydrology space. Up first is Gary Baker. He's our Hydromet manager. Covers for the hydrology segment for FTS, High Sierra, and OneRain. He's been in the hydrology market for about 25 years now, over 25 years, and has a great wealth of information. He'll be doing our introduction as well as focusing on our satellite options today. After Gary, we'll have James Logan. James is the CEO of both OneRain and High Sierra Electronics. He has close to 30 years of experience in the environmental monitoring space, and he has been with OneRain for about 16 years now. He has led designs for telemetry and software around the world, and he'll be focusing on radio-based telemetry options. And then finally, we have up Tom Ogden. He's our senior product manager for High Sierra. He has been with High Sierra since 1993, as well as been in the flood warning space since the early 80s. And Tom has a great wealth of information for the hydrology space and designing flood warning and hydrology networks. And he will be focusing on our IoT at the end of the presentation. And with that, I will pass it over to Gary, who will lead us through an introduction and go through our agenda. Gary, are you on?
I am on. Thanks, Charles. Thanks for all those that are joining us. I see a lot of people here that I've known for many years. Thanks for being with us. Today, in terms of our agenda, we're going to cover different options for telemetry. Leading into that, we're going to talk about monitoring systems and define what your system may look like, and then again focus on the monitoring or telemetry side of that. We're going to look at requirements as you're considering different types of equipment or different types of methodology of telemetry. We should probably consider a number of different requirements while making those decisions. We'll talk about the telemetry options and then do some summary in the end. by and large, the things that we're going to, the three different categories of telemetry that we're going to talk about are terrestrial radios. James is going to talk about those. We'll talk about satellite solutions as well. We'll talk about three different satellite solutions as well as the Internet of Things, which is kind of a newer buzzword. It's a newer technology, in some cases lower cost. We'll talk about some of the trade-offs with IoT as well. So looking forward, if we consider some of our different requirements for our site, it's been interesting. As we've talked about this, all of those on the panel, all of us over the years have been asked this type of question a number of times, and that is people might call up or ask you when you're visiting with them, what's the best type of telemetry to use? And the answer to that generally is there's a best per site and a best per network depending on what you're trying to accomplish. And so with that in mind, we've come up with a few of these questions to ask yourself, or a few requirements that you might consider. One is there an existing network that I already have established? And if so, how big is that? And do I want to add to that network, or do I want to create something in addition to that? Do I need my data to be real time? And we can talk about some of that as we go forward. How often do I need to measure my sensor, report my data, transmit it? How much data do I need to send? Is it small packets of data, or is it something much larger? What is my budget for my installation and equipment? What's the budget for ongoing data as we continue to send it in? Do I need that to be free of cost, or do I, can I afford to have to pay for that data? What type of coverage do I have for telemetry? In other words, is it a hard site to get out of, or is it relatively easy? Is it mission critical data? Do I absolutely need to make sure that my transmission happens when I expect it to happen? And then last, but certainly not least, this comes up all the time, and that is, what are my power requirements? And what kind of power can I get in there? In most cases, it will be battery and a solar panel. So that being said, we also put together a grid that we're going to show also in the end, populated after we've talked about these. You'll see on our top row at the top there, we have the different types of telemetry that we're going to cover and talk about in detail. And in the column over to the left are some different the different things or the categories that we're going to populate with under those the different telemetry options. As we talk about a monitoring system, we created this diagram as well, just spelling this out from the beginning to the end. Sensing, it just depends on the type of site that we're looking at. Is it a weather station? If it's a weather station, those parameters and those sensors might be different than simply a stream flow site or a flood site. Then we consider, do we want to log the data? And if so, then that will determine what kind of telemetry or logger we have out there. And then do we want to transmit the data? And that's, of course, what this webinar will be about, is transmitting telemetry. And that will determine as well, in a lot of cases, of how we'll receive the data. Do we already have a base station software out there? And what is it? And is that adequate as well and satisfactory to meet our needs? And then, of course, the data content and the decisions that we make, and how are we going to process that data. But again, by and large, today we're going to talk about the telemetry options. That being said, we're going to start talking about the terrestrial radio options, and start that with James Logan.
Hello, everybody. So we're going to talk about terrestrial radio options. There's three types that we'll discuss. Alert 2, which is the latest generation of alert technology. So we'll focus on what Alert 2 does. And that's a technology that's been in use in the U.S. for a long time and has been supported by the National Weather Service. We'll talk about MODBUS, which is a protocol that can be done over radio that is used by some agencies, and it's a technology that's typically called SCADA, which is used primarily in industrial applications for doing industrial and process control type things, but it's used as a telemetry for a few agencies in the U.S. that we work with. And then packet radio networks, which is another technology that allows you to communicate more as if all the sites are part of an Ethernet network. That's sort of how it behaves. They're essentially all on a network. So starting with Alert 2, it's widely used across the U.S. For real-time applications and primarily for flood warning and hydrology applications. It can be used for other things, but for the most part in the U.S., this is probably the 99% of its use is for flood warning and hydrology applications. It was designed to be backward compatible with Alert, which Alert has been in place since the early 1980s, and it's an older technology that needed to be replaced. And Alert 2 was designed to be both backward compatible and to provide all the modern conveniences of a modern telemetry platform. It's an open standard. It's being managed by the National Hydrologic Warning Council, and it's been supported by the National Weather Service. Almost every agency in the U.S. that has an Alert 2 network forwards all their data to the Weather Service to be part of their forecasting and warning process that they do, in addition to the local agency using it for their own purposes. It's real time, and real time in the Alert 2 context means that the data gets there between 30 seconds and 2 minutes after a data value gets recorded, and that time delay is typically related to how many gauges or sites you have on your network. So if your network has 200 sites, then there'll be longer latency, and if your network has 20 sites, then the latency can get very small, maybe even down to 5-second latency. It's a two-way protocol, and it also supports encryption, so you can do secure things with it. These are some features that have been added to the protocol recently, and they're now supported by the vendors. And so now you can use these capabilities for both two-way and encryption. It's a low power protocol, so the stations, almost all the stations that are out there are solar powered. Not all of them are, but the majority of them are. It transmits small data packets, so it's not a good protocol for transmitting large content. Like, it's not a good protocol for transmitting camera images, but it is a good protocol for transmitting environmental data, rain gauge data, stream gauge data, that type of data. And it's used, Alert 2 is primarily used on radio networks, but it is also supported over IP networks. So there are actually many vendors out there that have built interfaces so that they can send the data, for example, over a cellular data network. They can send Alert 2 content that way, and it can be sent through other means also. So Alert 2, it's primarily for measuring precipitation, water levels, and weather stations. That's what it's mainly used for. It's best when you have a line of sight system. So it's good for regional applications or local solutions, but it's not good if you have to build a national network of things. It's not good for that, but it's good if you're part of a city or a county where you can where all of your stuff is regionally located, and you can build a radio path between all the sites and where you want to collect the data. And it typically has infrastructure investment. So when you have a site that goes across a county, for example, you need to pay to have repeaters put in locations to bring the data out. one of the big advantages of Alert 2 is that the system it's very reliable. So once you build the system, during extreme events, there's no dependency on any outside resources. So this is a big strength of this technology, is that if you have an operations center that deals with, or emergency operations center, and you want the system to work, it'll always work even if the internet goes down, if the cell network goes down, if a hurricane's pounding and the streets are flooded. These systems work when in those extreme events, and you're not dependent on the internet being available or anything else. So it's a really robust technology for dealing with emergency applications. So, and when you build the networks, if they're built properly, then they'll be built with no single points of failure. So if they're designed properly and implemented properly, then that's part of the robustness of the system. MODBUS is another technology that's being used. We have a few of our clients that use it for their radio networks, and it's used, the protocol itself is used pretty widely. It's used both from sensors talking to a logger and from loggers actually transmitting over radio networks. The way that we've seen it implemented primarily is a pulled solution. So there'll be a central computer controlling an RTU that basically sends polling commands to all the sites in sequence and says, give me your data, site 1, give me your data, site 2, and it brings the data in. The agencies that we work with that use it primarily are creating time series data out of it, and the time series, the time interval is pretty dependent on how many gauges are on the network. So for example, to have 15 or 5-minute data, you'd have to make sure that you could pull all your sites within 5 minutes. So it's fairly complicated, but we have a few agencies that have like 500 sites. Or one agency we're working with has 500 sites that are using MODBUS, and they're pulling all the sites to produce 15-minute data, but it requires them to have 3 different radio frequencies, and it's sort of and they're actually starting to get full with the number of sites that they can pull because of the slots are filling up to support the 15-minute time steps. So MODBUS is it's primarily a system where you measure sensor values, and it's similar to the other systems that it requires line of sight radio. So they typically implement it with sort of a hub and spoke architecture where all the sites are around the spokes, and there's a hub that sort of does the polling. The need for line of sight is one of the major issues with a radio-based system like this, because you have to make sure that you can communicate from site to wherever you're collecting the data. MODBUS is not, from a radio protocol point of view, it's not a very secure thing. So with a MODBUS network, any of the entry points are its weakest links, and when you use radio protocol, basically every site is an entry point, and so is the central polling master that's pulling the data in. That packet radio is another protocol that is being used by a few agencies, and it has a lot of good things about it, and some things that are not as good about it. So it gives you the capabilities of a full network on it. So you can basically do anything you can do over Ethernet network, you can do over a packet radio network. It's typically more expensive because the hardware is more expensive that goes at all the locations. It can be complicated to implement. So it's just because the network, it doesn't necessarily have a hub and spoke network. It's basically the sites can communicate with each other, and they can act as repeaters for the data and route the data throughout the network. It is a real-time system, so the latency on a packet radio network is pretty minimal compared to some of the other protocols, because you don't have to wait as long for the data to get through. It does support two-way, because it's basically it supports everything you can do over an IP network. It is higher power because the radio is on all the time, So because radio has to be listening and transmitting all the time in a packet radio network. And it can support both small and large data content. So you can use small data, but you can also pass images and other things because of the way the packet radio works. And it's pretty flexible on how you can lay it out on a network. So it can follow along a long river, or it can be central with like a hub and spoke. So it can work several different ways. So now I'll hand it over to Gary to talk about some of the satellite options.
Thanks, James. The three different satellite options we're going to talk about is first GOES, and then we'll talk about Iridium, as well as Inmarsat, otherwise known in some cases as Orbcomm. First, we're going to talk about GOES. I just threw a quick diagram here together to talk about the path of where it begins and then where you receive your data. Of course, the bottom left is an indication of your gauge site out in the field, and it transmits from there up to the GOES satellite. From there, it's going to bounce either down to Wallops Island, where the data is first received, or it can be received over at Sioux Falls. If you receive it at Sioux Falls, or if it's received there, then you can easily capture it from their site, either from their website, or like the USGS pulls it off into their endless system from there, or it bounces up from Wallops. It can go to the DOMSAT satellite, and from there you can have your own local readout ground station that you can capture your data. But it's very quick. In capturing that data, it's extremely reliable. I did lay out, I grabbed this image as well, just giving you an indication of where exactly from the GOES West and the GOES East satellite in terms of coverage. You can tell from these two satellites, great coverage with North and Central and South America, as well as some of the other a little bit in some of the other countries, but some of the other countries also have their own satellite systems that work similarly off GOES. For instance, in India, they have INSAT, and it uses roughly the same transmitter. It's just certified different and a few other tweaks, but that gives you similar GOES access to some other parts of the world as well. Just a little bit of background how GOES works. In some cases, many on here probably have used GOES. There are some that have not. So just wanted to cover in briefly, and I have a picture here of a current GOES transmitter data logger, the LT1 that we make at FTS. You would get your data or your access to a GOES transmitter an approval through NESDIS. NESDIS, by the way, is a division of NOAA. NESDIS stands for National Environmental Satellite Data and Information Services. They actually manage the satellite systems. You apply for your access to it. From there, they'll give you a channel and an ID. The DCP, or the GOES transmitter, actually stores data in the buffer, and then when you're given a time slot by NESDIS, and when your time slot comes up, it will transmit the data that was stored in the buffer. For instance, many are given an hour window these days, and if you're logging your data every 15 minutes, those 15-minute readings will be stored in the buffer, and when your hour comes up, it would transmit those 4 measurements. That's done in the self-time channel. You can also be given access to a random channel, and the random channel is basically an event channel, meaning that you can set it up saying that if my stage gets to X value, then transmit, and so you can do that. And in some cases, there are many that are using that for alert type sites as well, not alert in the way that the actual acronym alert, but more of a warning type site. We move on to the next slide. I just threw this up here to touch briefly. Setting up a GOES transmitter is by and large, when NESDIS gives you your access IDs, they'll give you your ID, your channel, your baud rate, your transmission rate, and your window. And you just put those right into your data logger, your GOES transmitter. So all of those just have these boxes or these places where you put that information that they've given you, and you put it right into the transmitter itself, making it really quite simple. A couple of advantages and disadvantages for GOES. GOES, there's certainly probably the biggest advantage is it's free to use. For those that are using it, there is not an annual cost or anything like that to use the GOES satellite. So once you're granted access and given a channel and ID, it's free to use. It's extremely robust. It's been around for years and proven and established. So the advantage again is the random channel as well. So if someone wants to be able to transmit based on events, they can. Disadvantage that the equipment compared to some of the other telemetry options that we're talking about perhaps has a bigger upfront cost. But again, it's free to use. The other disadvantages, it's one way. I put up here access to using the GOES, but by and large, most people can get access, and we can help advise you how to get that as well. I just threw up a couple of pictures here of some GOES sites. You can see the Aggie antenna on a number of these. That is a more traditional GOES antenna, and I got a picture on the next slide that I want to show you as well. But one of the pictures as well on here, I threw this up here. It's a little bit of an older, the second one to the right, a little bit of an older unit that FTS that we made. But what I like about this picture is that a lot of people don't use GOES for systems such as groundwater or something of that nature. But FTS helped a group up in Canada do a large program and network of groundwater sites where they used GOES, and this is a picture of one of them. So it shows the flexibility of different sites. I like this site as well. This picture was sent to me by the USGS out of Truckee. You'll see that picture on the left, they actually have both of these antennas up there. They're hard to see, covered in snow, but the Aggie antenna obviously at the top, and then right below the solar panel, you'll see the EON GOES antenna that's made by FTS. The Aggie quit transmitting. It quit transmitting through that Aggie with all that snow, and the EON continued to transmit. As far as our next telemetry, we want to talk about Iridium briefly here, but Iridium is more of a commercial type satellite. GOES is managed by the government. Iridium is a commercial satellite, or satellites rather. There are 66 low orbiting satellites. They orbit at 476 miles from the Earth. They're going at 8 kilometers per second. They clear the Earth or cover the Earth in roughly 90 minutes. So they are whizzing past up there. When you transmit, you're going to transmit up to the satellite, and it's going to basically find the closest one at that given time. The message occurs, the latency is roughly 20 seconds. It's less than that. Global coverage, the coverage is fantastic. When you have 66 satellites up there, you can transmit data from about anywhere. You do get access to two-way communication, which is a nice advantage as well. Disadvantages here is you pay what you use. We'll talk about that a little bit more here in just a second. I like this diagram. This shows a couple of different types of telemetry sites down here at the lower left, shooting up to the Iridium satellite, and then it comes through your gateway at the bottom. And the gateway, by and large, determines how much you're going to pay and so forth, and who's going to help provide you with the data. So the two different satellites at the top are kind of an indication that these satellites are moving past you, and when you transmit, it'll hit the satellite that's above you at that time. Some of the advantages and disadvantages of Iridium. Again, in some cases, I threw up here the DoD gateway, which represents Department of Defense. And if you have access to the Department of Defense gateway, transmitting through that can be free in a lot of cases. Iridium is extremely robust and reliable. It's a great network, proven, and under some cases, it's two-way communication, which is great for, again, for satellite. The disadvantage is cost. The cost is quite expensive if you're not getting free access to it. It can be expensive. So if you want the two-way communications and you want all the advantages of Iridium, it does cost a bit. So the other satellite solution that we can provide at AEM is Inmarsat, or otherwise known as Orbcomm. And we've done a number of sites. I've got some pictures up here in just a moment. It is geostationary, so it's not the low orbiting. It's up 22,000+ miles from the Earth, and so it's actually rotating with the Earth, which if you lock in your beam when you install it and it locks in, you're not going to miss a transmission. Once you've locked into that satellite, unless something is tweaked at the site, you won't miss your transmission. It is also another pay-as-you-use, and so it's not a free service, but again, it's all about what you want and what your needs are. This just gives you an indication here through this map up of really the coverage. The coverage is great unless you're on the tips of the Earth. And I don't think anyone on this call is. So in terms of what we're looking for in this group, you'd have great coverage. Inmarsat is extremely robust, not prone to having storms get in the way of its transmissions. Network is established. Again, your latency is not an issue. It's 20 seconds, if not less. Geostationary, as we talked about, which makes it extremely reliable as well. Disadvantages, again, you pay as you go. So you pay for the data as you use it. So you want to use more data, it's going to cost you more money. So here's 4 pictures of some of our satellite installations that we've done. And I like the way we've titled this. It's mission critical for remote locations. You can see these sites are certainly out in the middle of nowhere, but they don't miss transmissions. They work very well for these users that are trying to get their data on the regular. So great installations and great locations. We'll turn the time over to Tom.
Thanks, Gary. So as we see, I'm going to be talking about the Internet of Things, and I'm sure everybody's been hearing this term a lot these days. Again, obviously, like the Internet, it's a fairly new technology compared to these others that we're speaking about. A lot of what we hear about, a lot of the protocols, Bluetooth, Wi-Fi, Zigbee, 6LoWPAN, these are more local areas, sometimes referred to as personal area networks, smart homes and things like that. What we're more interested in, covering larger areas would be LPWAN, so low power wide area networks, and cellular certainly fits into that category. We're going to look at mainly one of the LPWAN technologies, LoRaWAN, and we see on the right here a typical network where you've got nodes transmitting to a gateway that's transmitting up to the cloud, and that's not untypical for a IoT type network. So cellular has, we're going to look at advantages and disadvantages here, like we have been with the other technologies, and one of them is kind of demonstrated by the map on the right. I believe this is a Verizon coverage map, and while not every inch of the country is covered, certainly the vast majority of it is, and some of the areas that aren't covered there are covered by other cell services. So that demonstrates there's significant infrastructure in place already. So there's a nationwide backbone of communication that's installed and maintained by others. So that's one of the things you're paying for. You're not having to put in your own infrastructure network. There's you have the capability of transmitting large messages. So this would be like video. You're not going to be doing with most of these other technologies or even images, but cellular, it's basically unlimited, and of course you're going to pay for it, but you do have that capacity. If that's your need, then that could be a good solution for you. It is also the potential to cover large areas with a dispersed network of gauges. So earlier we were talking about, James was talking about alert technology, which is great for a city, county, or region where you might have a number of repeaters bringing the data into a central location. But if you have sites that are spread out tremendously, 20, 30 miles, and not a dense network, it doesn't really work in an alert type environment or a SCADA type environment. But cellular, given that wide network capability, it would be a good solution there. It's very power efficient when you're transmitting in a one-way mode. We have sites that are normally sleep or in low power mode, and when it's time to take a reading, power up, transmit a signal, and go back to sleep, and that's very power efficient. And as we I think I mentioned that it's also a two-way communication is available, just like cell phone communications. You've got the two-way communications. If you've got a video, for example, you could be issuing pan, tilt, zoom commands back to the camera and have it be responding basically in real time. Some of the downsides, like other commercial solutions, you've got the recurring cost. There's also signal fade during heavy rainfall events, and we're talking about hydrology data here. That some of the most important data you're looking for are during high rainfall events. So that could be a problem. If you've got marginal signal normally, you could be losing data during storms. We mentioned the two-way communication. If you are doing two-way, you're powered up all the time. Definitely heavier power consumption there, larger panel, more battery, etc. They're also typically in emergencies, which is, perhaps the time when you most need your data. There's a heavy network usage on the cell networks, and that could affect your data reliability. We've also, I'm out here in Northern California, and you've probably heard about the PGE power outages we've had here last year and expecting again this summer, and that affected cell performance. So we had some cell towers were actually down with the loss of AC, and some that were running on generators had lower signal powers. I had that at my house, and definitely less performance when they were running on generators. So those are some of the things to consider with cellular. A couple examples. I'm going to give you two examples. Both of them are hybrid solutions where we're using two different telemetry modes. And this is a state on the East Coast where they're a cooperator with the USGS in a large network of water level sites that the GS maintains for them. And what they wanted redundant data, and they also wanted more frequent data. So in this middle picture here, you see our data logger with this Sierra Wireless cell modem in there, and we're reading the SDI-12. Basically, we're in something called a listen-only mode, where the GOES DCP is reading the bubbler here, and as any reading comes across, they're doing 5-minute readings now to get that more frequent data. We're listening in on that, picking it up and transmitting, so they're getting 5-minute data. So just an example of how you might blend telemetry solutions. The next one here is another hybrid solution. You see on the map to the right here, all these yellow dots actually represent at least 3 locations. So this is in Texas. We're out in the hill country outside of San Antonio, and we're using VHF, so terrestrial radio alert communications between the gauging sites and triggering these flooded roadway warning sites up the road in each direction. And locally, we're using alert communications, but as you can see in the map, we've got back to their base station, and this is hill country, back to the base station is 80 miles from some of these sites. So what we're doing here is each of these subsystems includes a cellular gateway. So the data's coming into the cloud, into OneRain's contrail for display, alarming, and historical data, and also gives them the capability of communicating out to the sites. So here's an example where we're using the robust alert communication locally and tying into the base station with cell. So that gives us that dispersal of communication. And so now we're going to look at LPWANs. So LPWAN again is a low power wide area network, and some of the protocols is LoRaWAN, which is a long range wide area network, Sigfox, which I believe was the first of these back in the early 2000s, and then there's some 5G cellular protocols that are being developed. You know, most of the cellular data that's being sent is more like IP data. They're actually developing these small packets of data similar to these other protocols that will be utilizing the 5G networks. So again, they're obviously, as the name implies, it's long range. In urban environments, maybe a few kilometers, but over 10 kilometers in rural settings. And it really depends on its line of sight base. So depending on, can go significantly longer than that if you've got a significant elevation on your receive side or transmit site and no obstacles. Low power, there's some of these transceivers can run on small batteries for up to 20 years. So it's really designed to be low power and low cost as well. So the LPWANs, the simplified lightweight protocol reduces the complexity in the hardware design, and so it ends up in lower device costs, and it's also cheaper for the infrastructure. There's some of the infrastructure. Well, let's go on. We're going to talk about LoRaWAN. I think we've got where we've got so gateways. First off, there's a LoRaWAN. It's an open protocol that is, there's an international alliance, the LoRaWAN Alliance kind of oversees the protocol, and it's a network of providers and device developers. There are some public networks being installed, so it's somewhat like a cell network in that the gateways are out there installed by a third party, and you're just installing gauge sites, or you might be installing a private network where you're installing your own networks, and that way, yeah, well, just that they're public and private networks. Transmission distance, as I said, it could be up to and over 50 miles if you have true line of sight. Again, it's low power. It uses an adaptive transmission rate based on the connection. So it communicates with the gateway and gets confirmation acknowledgement back, and it can determine at what rate of transmission it's using a chirp spread spectrum technology, and it can spread out how wide those chirps are spread out, and the more it spreads it, the greater sensitivity at the receive end. So it determines the signal strength required to get the message through, and then uses that ongoing. So this diagram shows various types of end nodes or sensors and transmitters transmitting through a gateway that then goes through a network server, and the network server performs security checks. It filters duplicate messages, basically manages the network, and then forwards data to application servers. So in our case, it would be Contrail by OneRain. I've got an example coming up on the next slide here that would be using what we're transmitting through a private gateway into the Things network, which is the network server. But this is we're calling it REMS. It's a remote erosion monitoring system. On the left here in that cabinet up on the pole, we see the gateway is installed, and it's a levee erosion detection. So the intent is to detect in near real time levee erosion. On the right-hand side, we see a beacon that's about 3 inches in diameter and about a foot tall. Those are installed in a levee, and there would be a fairly large density of beacons implanted in stretches of the levee that are at risk for erosion. Erosion occurs, the beacon starts floating and transmitting every 10 seconds an ID signal that goes through the network, gets to Contrail, and we know exactly where that beacon was buried, the GPS location and depth, so that information is immediately sent out to key personnel, and then strategically based on the path availability, we would be placing gateways in proximity to these erosion sites so that we're ensured that we're going to pick up the signals. And then as we said, the gateway passes the signal on, and it's very, very quick, and the alarms go out. So that is an IoT solution that's kind of our first entry into IoTs. And now I think Gary's going to get back to looking at that chart and summarizing these options.
Thanks, Tom. Thanks, James. I did get a question on, and I just want to retrieve this, I suppose, now and clean it up. I did get a question on Iridium costing, or cost of Iridium to receive your data. I suppose I made the statement that it's free. Iridium is really not free unless you have access to the Department of Defense gateway, which is really used by the Army and so forth. If you're working with the Corps of Engineers, for instance, they have access to it. Other than that, it's really you pay as you go, and you pay for the data that you use. If you'd like to discuss further much like a lot of the things that we spoke about. We spoke about a lot of telemetry options today and a lot of information. We realize that in a lot of cases, not everyone will have retained all this information. If you'd like to talk about any particular site and your best options for those, we would love to chat with you about that. So at AEM, all of these options we can provide and consult with you and try to find out the best one for you. If we go back to this chart, let me just briefly talk about this, and we can also help you get one of these as well. But again, the top row are the telemetry options that we spoke about, and the left-hand column, some different things to consider when putting out a gauge. For instance, do you want real time? And again, based on the things we talked about, we've populated in there what is real time and what is not real time, and how we've defined that. And then we put equipment cost and then data cost. For instance, you see alert and SCADA is at no cost. The GOES is at no cost. But then you see, such as the Cell and Iridium and some of these others, they have costs associated with them. Some of it varies, and that's why we put from 0 to a number, because it varies how much data you're going to transmit, how often you're going to transmit. So again, we could consult with any of you if you like over some of these. Power requirements, for instance, we put dependent on some of those. Some of them we just know are lower or higher than others based on what they come out of the factory at. Some of it's dependent, again, on how often you transmit and how many sensors and so forth are connected to all of this. So some of it does vary, but the nature of some of these telemetry options are lower power versus higher power, and that's what we're trying to focus on here. So based on some of this, you can see a summary. We'd love to chat through any of these. If anyone would like some help or some consulting through this, we'd love to help with that. So with that, we're going to turn it back over to Charles.
All right, thank you, Gary. We're going to open it up for questions. We had some good conversations here. We certainly covered a lot of telemetry options. So there might need to be some clarifying questions, or if people have any follow-up questions, feel free to ask us. Again, just to reiterate what Gary said, we did cover a lot, and there is a lot within that summary slides. And kind of to echo what he said in the very beginning, each site and each need is unique. It depends on the agency, what they're trying to do. And so we would love to help you walk through some of these challenges and to help you find the best solution that works for you, regardless of where it fits on that spectrum and on that table. So I have up here, before we open it up, any questions, feel free to reach out to us. We have some general contact information here up at the top, including a general distribution group and some general phone numbers, as well as the speakers' email addresses. Feel free to reach out to them, tell them how much you enjoyed them speaking, or to ask a question. With that, I will peruse through the questions. It doesn't look like we have any follow-up questions. We do have just one clarifying, just to echo what Gary said. It looks like that DoD gateway may or may not be going away towards the end of this year. So that free mechanism may or may not be there anymore. So we can help walk through that if Iridium is of interest. And with that, if there's any follow-up questions, I will allow people to unmute themselves. And feel free to unmute yourself if you have any questions. And